Alright folks, back to line integrals, but now I want to look at the scalar definition of line integrals. Let's take a look. So, what is the scalar definition of a line integral? That's what we're going to be taking a look at today. Let's say I have some kind of a wire. Okay, and I want to find the total mass of this wire given its density, its mass density at every single point. So let me show you what I mean. The density of my wire at this exact location, okay, and let's call that function lowercase sigma. Okay, so that function lowercase sigma is going to be a function of my position x comma y. Okay, so it's going to tell me at this particular point you have this much mass or density, at this particular point you have this much mass density, at this particular point you have that much mass density, and if I add all of these up, I'm going to get the total mass of my wire. So let me show you what I mean. So if I have this much mass density at this point on the wire, I'm going to have how much mass density on this total wire is simply sigma xy times the small change in the length of the wire. Right, so if the change in the length of this wire over here is ds, the total mass of the wire at this point would be this much. Now you can imagine that I'd want to sum up all of the small masses, so I'd have sigma lowercase sigma xy delta s, and of course as I take the limit of this expression as the number of pieces go to infinity, I'm going to end up with my line integral, right? So all of this is going to collapse. All of this is going to collapse to what? The line integral over some path c of sigma x comma y ds, and that right there is the scalar definition of the line integral. So thank you for watching, and we'll see you next time.